You have been teased with this ray traced image since the first part. Are you ready to render this image? Or do you want to try different scenes without changing your project? Or to make all of this 7 times faster? I'm excited to tell you, so stay tuned. We are in the 5th part of this ray tracing tutorial series, and this one would be all about reflections. One meaning of reflection is when light hits a surface and returns from it. Another meaning is to consider a thought deeply. We'll be doing a bit of both here. Reflecting surfaces add beauty and realism to an image. In fact, it has become one of the defining features of ray traced images. But so far, we have been projecting a ray from our eye to the object and finding what its color is. But the ray does not stop there. In fact, the ray can bounce that object and probably hit another object. How it reflects depends on the laws of reflection. The main principle might be familiar to you from school days. The angle of incidence is equal to the angle of reflection. Fun fact, this law is also observed in many other places like carom coins, billiard balls, and even the first computer game, Pong. Since we are dealing with 3D vectors, we have a special formula to calculate the reflected ray. So once you have a reflected ray, you can find out where it hits and the color of that place where it hit. This is the exact same algorithm that we have been using so far. So a recursive call to the same function would do. Since most materials are not perfect mirrors, we can take a fraction of this color and mix it to the original color. Now next, we can again find out where this ray has hit, has bounced, and this process can continue indefinitely in a recursive manner. In fact, this is the beauty of the ray tracing algorithm, and this is the reason why it is so short. But for how long? In most cases, there are only a few objects in the scene to hit. But what if the light is bouncing off two objects like two mirrors facing each other? We might perform the recursion indefinitely. In Python, each time you call a function, it eats up small amount of stack memory. After a lot of function calls, you might end up with the famous or the infamous situation of stack overflow, which also incidentally is the name of a website which keeps millions of programmers stay employed. This is why we will limit our recursion to a maximum depth of say 3 or 5. After that, we will not find any more reflections. But this is okay for most images. Now, on to some reflective thoughts. While working on the coronavirus episode, I realized that it's a little awkward to open the main file, delete the ball scene, and write in the new code. I did not want to do this each time I wanted a new scene. The obvious way to solve it was to describe the scene in JSON. Since I implemented that, I did find a few issues. So I re-implemented that. There will be some thoughts about the pros and cons of both approaches. So first, let's look at the problem. Now we are at our 5th subproblem, which deals with reflections. Let's look at our requirements. We need to calculate how the reflected ray looks like, or towards which direction and position our reflected ray will be at, so that we can continue the ray tracing algorithm with that same reflected ray, just like we would have calculated with our original ray starting from the eye. Once we calculate the reflected ray, we repeat the ray tracing algorithm, and it goes on for a certain number of times, which we call as the maximum number of depth or the maximum depth. Typically this is 3 or 5. I find that 5 gives a reasonably realistic render. Now the question is, how do we calculate the reflected ray? Like I said, a ray has a position and a direction. Now the direction is the most tricky part. So all we have to do is use this simple formula to calculate the direction. Direction can be given if you know L, which is the direction of the light or the vector of the light which is hitting on the object, and N stands for the normal of the object at the position where the light touches the object. So it's like the hit position normal. So L minus 2 times L dot product of N times N should magically give you the direction. Now it's not magic, it's actually mathematically derivable, but I'll spare you the details, which is not very difficult if you know vector arithmetic. Now, what is the position of this reflected ray? Interestingly, the position of the reflected ray is the same as the hit position in theory, but we are adding this second term over here, plus N multiplied by delta, where N is the normal and delta is a very small number, like 0.0001. Why do we have the second term? The reason is quite simple. If you start at the same hit position for the reflected ray, then it is very likely that the algorithm will get confused that it again hit the object from where it started from. So to prevent the algorithm from calculating that as the hit position, we have to displace the ray along the direction of the normal in a small by a small amount. So that's why we use delta, which is a constant in this particular formula. It's practically the same as saying the hit position, but slightly displaced. Now, most of our scenes have been having a red ball in the center surrounded by nothing. But typically a scene would look more aesthetic if there are more objects in it. So this time I'm going to add some more objects, try to make it a little more interesting with a pink ball at the further end and a blue ball slightly towards you. And there will be a ground plane or a floor which is below these two balls, so that there will be something to reflect off, or there will be since we're implementing reflections, there will be a couple of objects to reflect off. Now you'll notice that in addition to a single light, this time we have another light, a second light source. So that's L1 and L2. This makes the lighting of the scene a little more aesthetic as well. Now I'll give you the exact positions and colors of this in a bit, but this is just to give you a rough idea of what scene we are trying to build here. Now you must be wondering, how do we create the floor? As you remember, our ray tracer is only capable of rendering spheres. This is not very difficult to figure out. The hint is that the Earth is just a giant sphere. Now, if you're standing on the Earth, it might feel like it's a flat surface. That is because the radius of the Earth is pretty big, not because the Earth is flat. So I'm not a flat earther. In case you are, I'm sorry if I have hurt your feelings, but spoiler alert, Earth is just a giant sphere, and all you need to create a plane surface, which you don't have to show the other side. If it's just the ground plane, in many ray tracers, in toy ray tracers, etc., what they do is just create a giant sphere. The next question you might be having is, if this is a ground plane, what would it look like, or what color it would be? In most ray tracers, they implement what is called a chessboard or a checkered pattern for the ground. And to align to that tradition, I would like to create a chessboard pattern. Now, if you remember, if you look at how we have implemented the ray tracer, we actually have a material class. And if you need to create a different kind of material with a different kind of pattern, all you need to do is subclass that particular material class. If you remember, that material class has just one member function, or mainly one member function called color at. So if you know what is the color at a particular position, you pretty much have nailed how to create that pattern. Now what I'm going to show you is interesting property of the chessboard pattern, which will help you implement that chessboard pattern. I have numbered, I've created a small chessboard figure over here and numbered all the rows from 1 onwards. So 1, 2, 3 rows, and all the columns from 1 onwards as well. 1, 2, 3, 4. If you start from the row number 1, which is an odd number, at every odd numbered position there is a black square. Now if you go down to row number 2, which is an even number, at every even numbered position there is a black square, and so on and so forth. So the way to implement this is quite simple. If you have an odd row and an odd column, or an even row and an even column, then you put a black color, and if it is otherwise, if they are not odd or even at the same time, it's a white square. Now please remember, this is not always going to be black and white. You could give two different colors, say dark brown and light brown. So you have to make that parameter passed when you're creating the material. This is so that black and white is quite boring, so sometimes you would like to give a slightly tinted color, like a wood finish, for these kind of materials. So just make those colors configurable. Now how does the scene look like in terms of numbers? If you want to reproduce the exact scene that I'm going to render, then it might be useful for you to copy these values or write down these values when you're seeing them on the screen, so that you get the exact same results. So the camera is positioned at this particular position. The blue ball is at this particular position. It has a radius of 0.6. It has a color of pure blue. And the pink ball is at this position. It has a radius of 0.6 and it has this color. The ground, as you would notice, is at a very large Y position. The Y coordinate is around 10,000.5, and correspondingly the radius is also 10,000. So it's only a 0.5 standing above the screen, which is perfect because it aligns to almost nearly the middle of the screen, which is basically where we want the horizon to be over here. And that kind of gives you the effect that it's a flat surface, whereas we are actually looking at the top half, or the top very little tip of the large sphere that's underneath, or which is concealed behind below the frame. And there are two colors for the chessboard, as I just mentioned. I'm just going to tweak the ambient and reflection so that it's not so glossy or reflective, as a floor is slightly dull than you would rather expect it to be. And then you'll have the first light at this position with a pure white color, the second light at this position with a slightly grayish color, and that's pretty much it. That's all the scene we need. If you would like bonus points, I would like the scene to be loaded via command line arguments, so that next time I need a different kind of scene, I do not need to change the main.py. All I need to do is send a different scene through the command line arguments, and it should pick it up from there. So these are the requirements. I strongly recommend you to try it on your own before you continue and watch how I'm going to code the solution. So try it. Welcome back. So I'll be taking you through my solution. Before I start coding, I'd like to have a clear idea of how I'm going to describe the scene. I had a dilemma between describing a scene as a JSON or an XML or a config file, or should I use a simple Python program and import that Python program. I'd like to call this as config versus Python as config. I'd like to show you the pros and cons of this approach, either of these approaches. First, I'd like to tell you that I implemented my first time when I tried to implement the ray tracer with a separate scene. I described the scene as a JSON file, and I created several JSON files for different scenes and tried to render them, and that's how my initial implementation went. I'd like to tell you some advantages of this approach. If you are not sure where these JSON files came from, for example, you want a ray tracer where, say, people are uploading scenes into your website and you're rendering it, then you cannot take a chance there. You cannot use Python scripts indiscriminately because it can run any unsafe code. So that's probably when you would use something like JSON, where it doesn't have unlimited programmatic ability or YAML files, which still has some ability, but you can create safe sandboxes. Next advantage is non-programmers can use it, so it might be something that you would want to give it to say a designer or an artist. And third is it's not tied to a programming language like Python. So for example, JavaScript can natively parse JSON files, and many other programming languages can read and write JSON files. Next, my second implementation was as a Python module, and I found a number of advantages, and I kind of solved many of the limitations I had with the first implementation. When I say Python module, what I mean is similar to how settings.py work in Django, where all the settings of a particular website are stored in a Python file. In fact, settings.py is nothing but a Python file with certain constants defined in it, and you can use it like a configuration file. DSL stands for domain specific languages. You can also store settings inside a mini language that you have created inside Python. What are the limitations I found with languages like JSON and YAML are kind of engineered into the specification itself. For example, deliberately JSON does not have any ability to have comments. This becomes difficult if I want to mark a particular sphere as a pink ball or as a blue ball or as a ground plane. I could use hacky ways of doing this by storing an underscore attribute as an internal comment, etc. But it seemed a bit too hacky to me. Second problem is about serialization and deserialization. For example, you want to read a number, you probably have to read it first as a string within double quotes, and then you have to convert it to a number. You have to check whether it is a proper number. You might have all sorts of null handling issues, and none had to be parsed, things like that. There could be bugs with the kind of serialization and deserialization you do because you didn't think about a common corner case or common case like that. The third problem is you are going to add a separate set of tools to say intend or lint or to parse your config files. For example, JSON files have this annoying ability to not work when it has a trailing comma in a list, which is perfectly valid in Python, but in JSON it makes it completely invalid. Now, JSON parsers do not give you a very proper line number based message, so you might have to install some sort of a tool which gives you error message, which is all adding to your complexity, adding to the kind of infrastructure you need to maintain your program, things like that. And the fourth one is, you might need a programming language at the end of the day to describe a scene, like we found for the coronavirus episode. The positioning of these spikes were all based on trigonometric functions, and it's not easy to implement that in a JSON file. In fact, I would say it's not possible to do that unless you have a program which generates a JSON file, which according to me defeats the entire purpose of having a config file if you have another program which generates the config file. So I also did some research on popular frameworks and libraries which implement this approach of using Python files as config or as setup files. So if you like we just talked about Django, if you look at setup tools, the setup is entirely defined inside setup.py, which is a Python file. Similarly, all these other examples where I found Python files are pretty common as settings. So my decision would be to use a Python module to describe my scene and import that in my main program. So that's what I'm going to do now. So let me remove all this. From our Corona episode. some gap here. I'm going to create an examples directory, and I'm going to create a file called twoballs.py. I'm going to copy a bunch of these things from here, remove all of them. We don't need those. I'll come back to the objects later. Now I'm going to assume that there is a material called something here, checkered material. Leave it at that. I'll define it in a minute. Now we have to create this checkered material. So I'll open up materials. .py and create a copy of this materials. So this would be color 1. That will be color 2. Based on that. And before I forget, I'm going to add one more property called reflection. So that's color 1 and color 2. Here we need to be careful. So dividing it, finding percentage of 2 is basically asking whether it's odd or even. That should be same as the position of z. This one need to shift by 0.5. So this is basically a programmatically derived pattern after some experimentation. So yours could be different. You might get a slightly different shifted pattern. It's just that my original scene had this pattern, so I'm just trying to copy this. So now we have a checkerboard pattern. Ambient is 0.2 because the entire plane might not be well lit. So I had to increase it from 0.05, which is the default, to 0.2. Reflection, I don't want a very shiny floor, so I made it a little dull. So that's why that's 0.2 as well. I had to import that. So hopefully the errors are done. Okay, coming to the main program. import lib is a very handy library to import modules, exactly the same way as Python would import it. If you want to compare it with two balls, I would like the scene to have the mod.camera. So it's like importing any other module like sys.path or something like that, os.path or something like that. So I'm importing this camera over here. So the same way I need to do for all the other arguments. So objects, lights, width and height. Next I need the engine to render it. Finally the image has to be written. Now here there is a little catch. If you write the image directly to mod.rendered image, it will be rendered in the same directory as the main.py. I want it to be in the directory as where the module is. So I just need to do change to that particular directory. So here is a os.ch dir for that. And this should be the directory os.path.dir name of mod.file. And just to be sure, I'm just going to turn this into an absolute path, os.path.abspath. So to import OS first. And now once you have changed the directory, it's easy, right? Last for the scene. If you notice, it will not be here, but if you do ls examples, there you have it. So let's open that. So there you have it. You have a checkerboard floor and you have these two balls which are slightly floating in the air. Now let's move on to making these reflections. Now I want you to go to the ray trace part of it. Just after color over here, just before returning the color. So this is where we would calculate the depth. So I want to calculate, add a depth here. Depth and then self dot max depth. is less than that, then you need to do this. Calculate the new array position equal to now max depth and minimum replace. I'll just define it over here. This is where we use the formula. Now all we are going to do is recursively call the ray trace function again, but before we do that we need to remember that the ray gets dimmed slightly because of bouncing. It loses some energy, the reflection loses some energy, and that's what we are going to reduce by, so that's called attenuation. So I'm going to say the reflected ray found by the reflection coefficient. Okay. Now the ray is the new ray. The scene is the same. The depth is depth plus 1. And the attenuation happens by the material of the object. So that should do it. No errors. So as you can see, the floor has a subtle reflection, the spheres have a good amount of reflection, and the light is reflected as well. So this is a beautiful example of how ray tracing works and gives you a realistic image. Next is a very important part of this segment. So I'm going to increase the size of this image to a somewhat reasonable value, and we'll see how much difference it makes in the rendering time, how slow the rendering time is. So these are half the dimensions of an HD 1080 by 1920 by 1080 pixels, full HD resolution. I'm going to run the example again. You would notice it's pretty slow. So that took a considerable amount of time. Let's look at what it rendered. Wow, the result is definitely worth the time. And you can see that it's much more detailed now. But look at the time it took. I mean, it's not even full HD and it took a long time. And now we are beginning to wonder what we started in the beginning of part 1, whether Python was the right language for doing this. So let me try to speed this up and show you how this can be done. So how do you make Python programmers faster? There are a lot of performance improvements, techniques, and ideas to do this, but I have a very simple rule of thumb, very crude, but you can think of it as a first pass. Is it a processor bound program? Then you have to try PyPy. If it is an IO bound program, try async IO. Now, what do you mean by processor bound? First, let me explain what is meant by IO bound. That will make it a little more easier. An IO bound program involves a lot of IO. So reading from disk, writing to disk, reading from the user, writing to the user, reading from the network, like downloading a file or making a request. All these things are beyond the processor. I mean, your computer is actually involved more talking to the ports rather than crunching numbers. So in those kind of programs, we actually try to use something called asynchronous programming. And I have an entire tutorial on asynchronous programming if you're interested due to async IO in Python 3. But if your program is more oriented towards doing number crunching all the time, then I would say use PyPy. So this is a perfect example of that, where the ray tracer is given an entire scene. It has to go through all the numbers in that scene. It has to do a lot of calculations for each pixel. The whole time it is not going to do any IO. It has everything in the memory. It has just to go through those numbers and do calculations. So PyPy is actually an optimizing compiler that is so fast that it's written in Python itself. If you know the C Python compiler, which is a regular Python compiler, is written in C, whereas PyPy is written in Python. Now let's try to run this very exact same program in PyPy 3. So PyPy has two major versions. One is called PyPy 2, which is the port of Python 2, and one is called PyPy 3, which is the port of Python 3. So PyPy 3 is a relatively less mature product, less mature at this point in time project. But I would say that since we are using Python 3 features, we cannot use PyPy 2. We have to use PyPy 3 itself. So let me show you running PyPy 3 for the same, and you can see how faster it is. Look at that. It's just zipping through it in no amount of time. It's like over by the end of 5 or 6 seconds. Now let's look at the output. It's exactly the same. So the same program was executed with the same output in a fraction of the time. How much time is the difference? So this is a graph I made when I was testing on my system. The CPython program took 57.88 seconds, whereas the PyPy program just took 8 seconds. So the speed up is actually 7 times. Imagine, that's actually a difference between if it takes 5 minutes for you to have a coffee, it could take 1 hour. PyPy 3 could be done when you're making a coffee, when a very complex scene is being rendered, and CPython 3 might take more than an hour to build the same scene. So PyPy 3 makes this entire project viable in Python. According to me, only when I discovered PyPy, I realized that a Python ray tracer is not a joke. It's actually possible, it's actually usable. And this is the biggest performance jump that you're going to see when you're running. So from this point onwards, I'm just going to use PyPy 3. I'm not going to use CPython. I'm going to run this ray tracer in PyPy 3. And I hope you enjoy the results and create new scenes. So send me your scenes. I'd like to see those scenes, what you create out of this ray tracer. It's pretty capable. It is having a good amount of realism in it. And I hope you stay tuned for the next part. So far, I've covered most of the ray tracing techniques that I wanted to cover in this series. We also improved the performance of the Python program dramatically by using PyPy. But there are still more options or techniques to improve the performance. The next part would be about that.